Holding neither. The uncertainty of all claims to knowledge.
That's true. That's kind of what I do here, in a sense.
You sit there and you start reading quasi and pseudo and kinda.
Yeah. Yeah, I mean, the vastity of the, I guess, signal processing literature that I have barely scratched, in working on this for 3 years, that I got a little bit close to. To me, it's overwhelming.
Well,
it's just
and then on top of everything else,
and the formality.
There are half a dozen different primary subgroups that don't talk to each other.
True.
So that the words that they use, you almost have to have a Rosetta Stone.
Exactly. Yeah, absolutely. And once you're inside, they actually use them freely, because once they're in the group, they actually enjoy the richness of possible path that the language can take.
Sure.
So it seems like from the outside it would always be wrong in choosing one, but inside they really take pride in the flexibility, in the fluidity of the language. So to me it's been like thrilling, although just humbling in this sense of like, wow. I mean, if in 10 years I can then penetrate it to a point of having that level of, not even just like a fraction of that level of comfort with that rigor, with the language, it would make me happy. But even them just using this thing, so let's say using it smartly, you're using it with awareness, it's just, I don't know, I find it a lot of fun.
All my signal processing stuff from the point of view of stochastic processes. And then all of a sudden image analysis comes along, and then this, and then that.
Yeah, this is more like the part that goes into image, so I got more familiar with that, but then there's all part that I'm missing, I say openly, is the statistical interpretation of signal processing. To me, it's absolutely fascinating. Besides, I'm not particularly versed in that field to start with. It's one of the things that I'm trying to incorporate, one little drop at a time. But to me, what is fascinating is the description of deterministic stuff, like the way I see linear algebra in statistical language.
Yes.
It's absolutely fascinating.
You just need to get a book on measure theory and realize that that's the space you're working in, and then all the knowledge that you have from deterministic math applies.
Okay.
Pick up a book on mathematics and read it, and get your head around that, and then all of a sudden you're going to see that it's just a different space you're working in. So, and then make it even worse, you've got an information theory.
Right.
And that's kind of halfway in between.
It's combinatorial as well.
So, like
but
fractional derivatives.
Oh yeah, no, not now. Yeah, I remember that when I was taking ODE class, graduate level ODE class, and the guy covered for a couple of weeks stochastic ODEs, and so the Euler-Moriyama kind of integration. And then it was fascinating and disturbing that actually things work. I mean, essentially the structure of the integrator was identical, just to be reinterpreted in light of that. But I have to be honest. I mean, there was some difficulty in wrapping my head around. And around the parallelism, I was kind of almost more comfortable with the lack of parallelism.
So do you understand?
I understand.
Yeah.
False beliefs. Sure, that's where you get something that looks like diffusion. Because if you're the way you meshed your domain, you can actually. The way I convince myself is that I view
This guy.
Oh, someone else.
But that lady over there, second row, she will take care of the Q&A at the end. Yeah, okay, yes, she knows.
The way I made sense of both of you and went through and looked at what happens is the finite difference equation. I read at one scale, now I looked at a much finer version and said, what is happening? And you can say, oh, I see what's happening.
The other way of doing it.
Yeah.
So,
Yes.
the reason I'm developed this stochastic and shows the limit of the stochastic model. The stochastic model has enormous. And it's not till the conclusions he said it's not the same as what you see.
Anyway. Thank you. Diagnostics.
The reason I'm asking this is like this guy. I said,
But it doesn't explain why it's not.
and I'm going to say in my review, it's a great So remember when Kimberly alive, right, you've got 5 minutes left.
I have to talk to her. Very urgent. Thank you. Yeah.
So I'm probably
Yeah, Sonia is the one, master of ceremony, so you should ask for her when to start.
As soon as you finish, maybe even before I'm going to have to leave.
Yeah, but she'll give you the even now, time-wise. Here and there. I don't. Hello. Here. Just say something. Give up in the middle. Give up in the middle.
I think we'll go ahead and get started. So today our speaker for the Warren seminar is our own Stefano Gonella. Stefano has been with us for about 4 or 5 years. He did his PhD in Model-Agnostic in aerospace engineering and his postdoc at Northwestern. And just a quick comment before we start. It's a well-known sociological fact that people's pets resemble themselves. So the pet, when you look at the guy who owns a dog looks exactly like him. And it's also been said that's true of professors, that their research kind of blends in with the person themselves. And people that know Stefano is always trying to, that's my seat, please. They always say that they look like their research. And anyone that knows Stefano is always trying to find new and innovative ways of looking at a problem in a way that's never been seen before. And as you'll see from his research topic today, it's exactly how it's going to be. Thank you.
Thank you, Vaughn, for the cryptic but intriguing introduction. Thank you all for being here. Can you hear me fine? Yes? Okay, so today I'm really excited to share with you the results of this work that I've been involved with for the past few years. And that is our own take on the problem of structural diagnostics. And we have devised an approach to the problem that somehow sits at the intersection between two fields. On one hand, mechanics, in particular wave mechanics, and on the other hand, signal processing, and more specifically, image processing and machine learning. This is a project that I've been working on with my colleague Jarvis Haupt from the Department of Electrical and Computer Engineering here at the U. A collaboration that started almost serendipitously over lunch a couple of 3-4 years ago as soon as we met. We were talking about our research interests, and we identified this intriguing intersection between our apparently orthogonal research interests. And at that time I had a vision of this problem I wanted to tackle, and it looked like that approach would actually be perfect for the job. And since then, it has blossomed into a very fruitful collaboration, and it's been nothing but thrilling, really exhilarating to work on this project. And this is also the work of my student, Jeff Drews, who's sitting in the audience right in the back, and you will see plenty of his results, especially in the part of the talk that pertains to sparse coding and dictionary learning. So I jumped straight into a motivation, and try to put the problem in context. So we work in the grand realm of NDE, non-destructive evaluation, or structural diagnostics problem, in particular what we call wave-based diagnostics. And this is the paradigm. We have a medium, and somewhere we say that there is an anomaly. Anomaly is a vague word. We choose it on purpose to be vague because it could be anything. It could be inclusions, soft or hard. It could be defects, damage zones. And then we excite a wave, we induce a wave in the medium, we let the wave propagate and then interact with the anomaly. And then when the interaction occurs, we have a scatter wave field. And then we try to sense the wave field at different location and try to infer something about the anomaly. Position, first of all, and then maybe even something about size and shape, if we are lucky. The classical methods for wave-based diagnostics fall into two categories. Typically, we talk about pitch catch and pulse echo method. The names are self-explanatory. In a sense, with pitch catch, I send a wave, I let it interact with the anomaly, and then I catch it somewhere downstream, so to speak. And then I will have the signature of what I send in, as well as the signature of some scattering event that has taken place. Even more interesting and more widespread is the so-called pulse echo, where I actuate here, and then I let the wave interact with the anomaly, and then I receive the signal of the reflected wave. And then here I can calculate the time of flight that it takes for the wave to go all the way to the anomaly and back. And then if I know the group velocity of the material, which is a material property, then I can infer the distance, the radial distance from the transducer to the anomaly. So what happens is that if I work with a well-behaved medium, I have this situation that if I have like one sensor that I use as both transducer and sensor, excuse me, I have a transducer that I use both as actuator and sensor, then I have, once I identify this radial distance, then the defect can be anywhere on the circle. But then if I work with 3 transducers, I can see that I can triangulate the anomaly exactly because I have a unique intersection of the 3 circles. So what happens is that triangulation is achievable under these conditions using parsimonious data. So I only need few sensors, ideally 3. Then people in practice actually use more than 3 because they filter out error by having some redundancy in the sensing. But what if I consider a situation like this, where now I have my medium, and I have some islands where the material properties may be different. I'm not aware if they exist, I'm not aware how much they stretch in the domain, I'm not aware of the material properties might be in there, but they definitely affect the way wave propagation occurs. And my algorithm doesn't have any awareness of their existence or their characteristics. Then this triangulation may be impossible or faulty, because the time of flight would be authentic. They would reflect the presence of those islands with different material properties. But my conversion of times of flight into distances, which is affected by faulty knowledge of material properties, would fall short. So if I have materials that, for example, has undergone some severe material degradation over large islands of the domain, or material that has an inherent internal complexity that I'm not capable of modeling, then all this paradigm falls apart. On the other hand of the spectrum, we have different sets of techniques that involve non-parsimonious data use, but massive data use. So we are involving what we call dense spatial sampling. That is the ability to measure the wave field at a multitude of sensing locations. And this can be done in a pretty agile fashion nowadays using sensing devices like scanning laser vibrometers. And I'm going to open a digression right here, parenthesis, to tell you what a laser vibrometer is very quickly and what it can do for us. Essentially, a laser Doppler vibrometer is a sensing system that allows to perform non-contact measurement of the velocity of points that belong to the surface of a vibrating object. The principle is the Doppler effect. So I send a laser beam against an object, the laser beam is reflected back, and then if that point that has been hit by the laser beam is moving at a certain velocity in the direction of the laser beam, there is a shifting frequency in the reflected laser beam. That is all detected by the electronics of the system, and then I can infer what the velocity of that point is. The first generation was called single point vibrometer. So I only had one laser beam, so I could only detect the velocity at one particular point. Then came the second generation, the so-called scanning laser Doppler vibrometer, or SLDV. The idea is I have a scanning head, and I can move the laser beam around in space. So I can predefine a scanning grid on the surface of an object, and then I can sense at all the points that are the grid points of the grid. And then came the third generation, which is what we have in the lab, which is the 3D SLDV. Now I have 3 scanning heads, each one sends a laser beam, and I let the laser beams coalesce or converge at each measurement point. In this fashion, I can detect the 3 components of the velocity vector at each location that allows me to resolve both out-of-plane motion as well as in-plane motion. So in summary, the features of the system are that that is non-intrusive, because it's non-contact measurement. I can have reconfigurable sensing, because I can change the pattern of these grids. I can have dense sensing, because I can stick a bunch of points in a certain given area. And finally, I can perform remote sensing, so I can sensing from far away, if needed. When this all started, it started about 10-15 years ago, and it was pioneered by the aerospace industry. This is an example, for example, of structural health monitoring performed on the tail surfaces of a military aircraft by means of a laser vibrometer. Then the energy industry picked up, and there's a lot of work that has been done on the structural health monitoring or diagnostics at the depot level of power wind turbines. And this is an example right here. And a bit more recently, the civil engineering community also picked up this technology, and for the structural dynamics monitoring and health monitoring of civil infrastructures. These are a few examples. This is, for example, the assessment of the surface health of a concrete block. Then here we have the inspection of steel elements in what they call megatruss building structures. This is interesting. This is the monitoring of the stability of stay cables in bridges. This is an example of this Daicho Bridge in Canada, which is built in an area that has very strong winds, and so there are strong issues with the stability of these cables. And then also recently applied to masonry structures. This is the study of adhesion problems in a masonry structure where there are older and newer bricks, and there are some problems of adhesion and contact between the different phases This was like a tower, an old tower that has been repaired with new brick material. Okay, so let's see what is a wave field, what a wave field that we acquire with the laser vibrometer would look like. Well, this is a snapshot of an experimental wave field obtained by Michaels and co-workers. This is a Lamb wave in a thin plate, and we see all the nice features of the wave field, and as you pay attention, we also see the visual signature of a few scatterers that are embedded in the plate. Now, there are pros and cons of using laser vibrometry. In a sense, we need to perform a scan, which can be a time-consuming operation. And also, even in this day and age, with all the advances in laser technology, the systems are not trivial to deploy. They still occupy a certain volume. So in a sense, using laser vibrometers may be less practical than conventional techniques based on sparse sensors like accelerometers for what we call online or in situ structural health monitoring. But on the other end of the coin, we have this beautiful data richness, spatial data richness that we can exploit. And the claim that I'm making today, and I'll try to demonstrate, is that this data richness can somehow compensate for a lack of a physical model, which is the problem that I was explaining earlier. If I have big damage zones, or if I have internal complexity in the material that I cannot model explicitly. So this would grant us the robustness to work with media that have unknown or unreliable material properties. For example, as a result of complexity, heterogeneity, or extended damage zones. So what is that we're trying to do with these assets? Well, the objective is to develop data-driven diagnostics methodologies that involve criteria of sparsity and that use approaches that are imported from the communities of signal and image processing and also machine learning, ML. And we have a requirement, so a series of attributes that we would like our methods to possess. We would like our analysis to be automated, so implemented on the computer, bypassing the human inspection component. But at the same time, we recognize that humans have an innate ability when they look at stuff to find anomalous stuff. And therefore, we would like to mimic certain human cognitive processes that we think have important attributes and incorporate them in our algorithms. We would like the methods to be unsupervised in a machine learning sense, which means that they should not require databases or training sets. We only use the current data for the current simulation or experiment. And finally, and this was in the title as well, we would like the methods to be agnostic, or more precisely model-agnostic. So we should not require any a priori knowledge of the material behavior or constitutive model. And that is what would give us the robustness to work with the material that have complexity of some type. We have worked on 3 or 4 different techniques to do this, and now I'm presenting 2 of them. The first one is based on criteria of saliency, and I will refer to this as a quasi-agnostic method, and you'll understand why. And the second one is based on concept of sparse coding and dictionary learning, and I will refer to this as a fully agnostic approach, or quasi-fully agnostic, maybe. Before we start, just one more, a couple of words about the importance. I made a case for why it's important to be agnostic. Let me say a few things about why it's important to be automated. Well, ideally, at the end of the day, we would like to, at some point, develop something like this, what I call a multi-resolution diagnostic strategy, based on nested scans with increasing levels of refinement. For example, the idea is to start with something like this. I'm going after this 2 defect. I perform a coarse grid scan. I know I'm not demanding that I get the defect just from this coarse grids, but at least I might be able to say what are the hot spots, the regions where I have the highest likelihood to have the defect. And then at the next level of refinement, I would just concentrate my attention on these 2 regions and refine the grid locally. And then keep doing this nesting and refinement operation until I converge and I pinpoint the actual defects. So what I would need is algorithms to drive the adaptivity, to drive this adaptive process that guide me from this initial scenario to this final scenario. Okay, saliency analysis. Let me start by introducing what saliency means. Well, saliency is defined as the perceptive quality which makes certain observable features stand out with respect to their neighbors. And I like to illustrate the idea with a little game. This is taken from this blog on machine learning called Salient Green, and it uses a very famous set of data from a seminal paper in computer science by Laurent et and co-workers. The idea is we have this 2 collection of rods, some red, some green, some tilted to the right, some tilted to the left. And we have there to identify the salient one, that is the outlier. And if we spend some time looking at this figure, we see that this is the winner, because it's the only one among the red that is tilted to the right and not to the left. Then we could do the same also working on a smaller sample, and we would come up with the same conclusion, perhaps even a bit faster, because we would have to visually scan less objects. And then we could do that on an even smaller sample right here, and we would still get the right answer. But interesting enough, check what would happen if we would work with an even smaller sample. If we work with this sample, we would actually pick this one as the winner, because it's the only one tilted to the left, but globally it would be the wrong answer. If I pick an even smaller one, then I would see that I have an ambiguity. I don't know which one to pick. They are both equally salient, which is the same thing of saying that they are equally non-salient. So the conclusion is essentially that saliency is not an intrinsic property of a certain feature, but a property of the feature with respect to its surrounding. And somehow the ability to detect salient features depend upon the size of the samples that I'm considering. And you will see the counterpart of this in the wave problem that will come next. When I started working on salience, I was very excited because it looked like we were the first guys to apply it to mechanics. But then we look around in other fields and everybody loved saliency. It seems like it's ubiquitous across engineering and science. For example, to do moving objects in video feeds. For example, to design image compression algorithms. This is, for example, the comparison of an image compression algorithm, standard one, and one based on saliency. You see that this one does a much better job at preserving the important features of the image, especially at high levels of compression. Then the medical field. For example, people are starting to do some diagnostics of body abnormalities just by looking at medical scans. And this one is probably the most fascinating for me, from the field of neuropsychology. People would essentially ask patients to stare at images, and then they would track their eye movement, their eye motion, to see what details of the image they concentrate their attention on. And then they would construct these saliency maps that tells us what are the details that are found most important by the individuals that are participating to the experiment. And it is found that there are very different images, very different maps between so-called normal patients and patients affected by, for example, autism disorders. Okay, now, what is salient in a wave field? Why is this interesting for us? Well, let's look, for example, at this case. This is a result of a FEM simulation. This is a flexural wave in a 2D thin plate. We have an excitation here out of plane, and this is the wave front at a certain, this is a snapshot of the wave at a frozen time instant. And then we have three scatterers, and we see these halos, which the ring patterns, which represent the scattering event. Now, the true salient features, the one that we are after, are the circular features that are associated with the scattering events. But then I have also to compete with a bunch of competing sources of saliency, spurious ones, that I don't want to pick up. For example, reflections from the boundary. But even more importantly, more important than the reflections from the boundaries is a bigger enemy that we have. The fact that if we zoom out and we look at the entire wave field, we see that the propagating wavefront, the crest itself, is like a massive moving salient feature with respect to the rest of the domain, where there is no wave at all. So we don't want to pick that up. We want to pick up only these particular features. So what we perform, we try to remove this bias in the analysis by performing what we call a wave alignment, where essentially we try to virtually replicate the same virtual wave conditions at every location in the domain. Let me show you how we do this numerically. We start with our domain, and it is n1 by n2 nodes, and then we have capital T time instance. And we perform a partition of the domain into regions, n1 tilde by n2 tilde. Now, the big data cube is the one that contains information at all time instance for all the points, and there's this big data cube n1 by n2 by capital T. And here, the blue one is the regional data cube. So the data cube that that pertains to one region only. But now what we do is, instead of considering all the time instance for a certain region, we only consider the time instance that correspond to the time window in which we presume that the wave will travel through that particular region. And as you see, for every region, we have a certain small regional data cube that is shifted in time proportionally to the distance of that region from the actuation point. So instead of having one big data cube, we have this cascade of small regional data cubes. What happens to the wave field? Instead of having a frozen snapshot, we have this thing right here, which we call a jigsaw wave field, where essentially we have a collection of small regional data sample for every region at different time instance and collapse into one single 2D object. Now, how do we do this particular shifting in time? Well, we use some time-of-flight calculations. And here is where you could say, well, now you're using the group velocity of the material. You're almost violating the agnostic paradigm that you're trying to parade. And what I claim here, and I'll try to convince you with some examples, is that that is partially true, but I can actually live with a very crude estimate of the group velocity, something that has almost no awareness of the complexity of the material, and in some cases I can do a pretty good job. Because I'm not using it to triangulate the anomalies per se, I'm just using it to perform this alignment of the wave field. Okay, a couple of slides of modeling, bear with me. The first one is philosophical, the second one is more pragmatic, just to give you a sense of the mathematics that go into it. We model saliency as a generalization of sparsity. So we start with an assumption. We say, let's assume that all the regions in the domain that are sufficiently far from an anomaly exhibit some typical behavior, which is unknown. The behavior of the bulk of the response, as if the anomalies were not in the picture at all. On the contrary, the regions that are very close to anomaly exhibit an atypical behavior, like an outlier behavior, which is also unknown. Let's assume we could construct a feature matrix, let's call it X, organized in this fashion. The entries are either 0 or 1 according to whether we are in an anomaly-free region or in the presence of an anomaly. If we had such a feature matrix, game over, we would be done. This would be a sparse matrix, we look at it and we would have an intrinsic map of where the anomalies are. But we don't have such a thing, it's an abstract quantity. What we need to do is construct something from the available data that has the same sparsity structure of X and that serves as a proxy of X. This is the way we go around the problem. Okay, let's start from the regional data. This is all the data from the IJ region in the domain at a certain time instant, but we can forget about that for a second. And let's assume that we can identify an R-dimensional linear subspace that well approximates the data inside all the anomaly-free regions. So that is a linear subspace that well describes the bulk of the response. And then we project the regional data through some projection operator onto this linear subspace. Then we construct this matrix. You see the ij entry of this matrix is nothing but some Euclidean norm of the residual between the original regional data and the projected data. Now, if you follow a little bit what I said here, you will see that this Z matrix will have only significant non-zero entries at positions corresponding to where we have an anomaly. So it will be sparse. It will have the same sparsity level of X. It will be constructed from the available data. And so it will give us a map of where the anomalies are. So it will be the sparse proxy of the feature matrix that I was invoking. But the question is just moved away. The question becomes, how do I find this linear subspace? So this is how we do it mathematically. We recast the problem as what we call a low rank plus outlier model. That is, we construct this matrix M, and now this matrix M has as many columns as the regions. Each column contains the vectorized data from that region. As if I take all my regional data, make an array for each one of them, and stack them as the column of the matrix. Then I propose this decomposition of the matrix into a low-rank approximation, which captures the bulk part of the response, and an outlier matrix, a residual. And I want it to be column sparse. So I want only a few columns of that matrix C to be non-zero. And they will correlate very well with the salient regions in the domain. How do we find the low-rank approximation? By the solution of this optimization problem, where we search among all the matrices M that have rank less than R, which is a value that we set, the one that minimizes the residual with respect to the original data matrix. Good news for us is that the solution of this optimization problem can be done in a pretty agile fashion through linear algebra criteria by the solution of a singular value decomposition problem. So we take the singular value decomposition of M, we take out the singular value matrix, and we truncate it. So we only retain the R largest singular values, and we zero all the others. We put the truncated singular value matrix back in the decomposition, and here we have our low-rank approximation. Then we subtract the low-rank approximation from the original matrix, and we have the column sparse one. We inspect the columns of C, we see which ones are big, which one have a lot of energy, and they give us the position of the regions where we have anomalies. And then we repeat this business for all the different time instants. But the question is, how do I pick the rank R? Well, the good news is that I don't have to pick it. The data itself can give us a recipe to find it. I just look at what we call the plot of the singular values. And I see that upon a certain level, beyond a certain level, the singular value becomes small. That means that their contribution to the particular significance of the function becomes negligible. This is what people call the knee of the singular value plot. And so I decide to take the knee as my truncation point, and I only retain the singular values that are to the left of it. So in a sense, the data itself is educated enough to tell us where to truncate, and in other words, to discriminate between what is typical and what is salient in the wave behavior. All right. Let's see how it works. This is a problem. Wave field, 3 scatterers. These are 3 saliency maps that we obtain with this procedure at 3 different time instants. You see that primarily we have 3 regions that win. We can also look at a global or aggregated saliency map, which is right here. These are the 3 regions that are consistently found salient, or most consistently found salient. If we take the histogram plot and superimpose it to our Jigsaw Ray Field, we see that now we have identified these 3 regions as winners, and they correlate very well with the scatterers. They, in fact, encapsulate the scatterers. 16 by 16 seems to be a pretty good partition because it keeps the size of the sample sufficiently big and interesting from a data standpoint. But I can also try to work with a 32 by 32 partition. You see, of course, that the regions are smaller, so I am more accurate at pinpointing the right location of the scatterers. However, I pay the price because now the sample size gets small. Remember our original example. We start having some ambiguity that creeps in, and we start having some false positives, mostly here by the origin. Our speculation is that the feature that is picked up here is the high curvature of the wave crest that start playing the role of a salient feature that competes with the ones that we're going after. Another example, line defect, representative, for example, of a crack or a region of debonding. With an 8 by 8 partition, we do a pretty coarse job where we are still able to locate the 2 extremes of the line defect. With a 16 by 16 partition, we actually reconstruct the entire path, and we have a few outlier activity right here around the crack. And with 32 by 32, we also estimate the length of the crack pretty well, and we start getting a sense of what is the thickness of the area of influence of the defect. I'm going to skip on this one in the interest of time, and I'm going to jump to this case, to this problem, which is where I show that we are not violating the agnostic paradigm. So here we are taking a domain, very similar, and we have an anomaly right here, and now I'm introducing in the simulation these 2 L-shaped regions where I drop by 30% the Young's modulus of the material. Now, the algorithm is not aware of the presence of these inclusions. Okay, so I'm only using the group velocity of the pristine material in the procedure that I just showed. And regardless of this perturbation of the material properties, I'm still able to pretty well identify the hotspot where the scatterer is located. I think the next example is even more interesting. So here I am introducing a chessboard pattern in the material property distribution, which means that I am dropping by 50%, in this case, the Young's modulus in every one of the darker squares. And as you can see, you can visually see the mess that happens, the signature of the heavy wave field distortion that we obtain. Nonetheless, with a little bit of false positive, we're still able to identify pretty successfully the region that contains the anomaly. And I want to emphasize again that the algorithm has no awareness of this correction of the material properties. And if I had to apply a time of flight calculation-based triangulation to this type of domain, I would definitely be off by quite a bit. And finally, one experimental example. We have only one set for this particular technique, a bit more for the next one. So we have an aluminum plate in the lab, and we, in the back, we have an excitation using this P-wave generator in the midpoint of the rear face. And then also we have an anomaly, which is at this location, but it's not in the front. It's on the rear face. It's a shallow hole or a partial hole. So like a depression of thickness confined within the circular area. And we are scanning this portion of the front face, which is, for all intents and purposes, pristine. And this is a picture of our laser vibrometer with the 3 scanning heads that are mounted on this high-precision tripod. And this is what we get. This is the wave field, and after inspection of the characteristic wavelength and the velocity, we recognize it to be the first antisymmetric or A0 Lamb wave mode. And this is what we obtain with the algorithm. With a 16 by 16 partition, we have a pretty good pinpointing of the region where that shallow hole was. With a 32 by 32 partition, we do an even better job at triangulating it correctly. However, we start having quite a bit of false positive positive activity by the origin. And also, unfortunately, I'm not happy about this, one false positive far from the origin. A posteriori, we went back and checked what the data looked like there, and it turned out it was an extremely noisy patch. For some reason, the acquisition was just faulty there. And of course, the algorithm interpreted as anomalous data. And then finally, I also tried to do some subsampling. So for example, only retaining 25% of the scan points, and you see that the wave field looks a lot more distorted. Nonetheless, we are able to identify the hotspot pretty well. So I think this concludes the first part of the talk, which is the account of this first technique. And I'm ready to jump into the second and most recent one. Yes, probably you want to have the mic, though.
Oh, probably it's better.
Later? Okay, we do it later. Don't forget it. So the idea, here we use concepts of sparse coding and dictionary learning. So I'll try by explaining what we mean by dictionary and what we mean by dictionary learning. When we say dictionary, we essentially mean a basis, so a collection of basis functions. So finding a representation of data in terms of a dictionary consists of projecting the data on a certain basis. And I would like to point out that it's a very common procedure that we do all the time. For example, whenever we take the discrete Fourier transform of a certain signal. Here we have a signal, which is an array, and then we're trying to obtain the transform signal, which is another array, and what's in between is the DFT matrix, which is a matrix whose columns are digitized harmonic functions, such that if I have, for example, one signal that corresponds to one of the columns, then I have non-zero elements only at one particular location and zero everywhere else. Same thing for this other example right here. But otherwise, more in general, I have a blend of all these different column contributions into the signal. And this array gives us the coefficient of influence of these different harmonic contributions into the main signal. So we can see the DFT matrix as the dictionary for the DFT problem. But there's a problem that is even closer to us in structural dynamics. And that is the problem of modal analysis. And I would like to explain dictionary learning as a natural extension or generalization of modal analysis. What do we do in modal analysis? Well, we say that when we have the response of a system, which is function of space and time, we can write it in terms of a summation of modes, where we have mode shapes, which are functions of space only. And then we have these modal coordinates, which are harmonic functions that give us the harmonic fluctuation of the so-called modal coordinates. And then we have modal amplitudes, which typically are to be determined from the initial conditions of the problem. If we have a discrete system that has n degrees of freedom, which is sampled at capital T time instance, then this becomes this, where now we have an array that represents the response, and we have this vectorized mode shapes, and now the summation only has capital N terms. So that is, the number of modes corresponds to the number of degrees of freedom. This representation can also be recast in matrix form as a matrix factorization, where X is the response matrix, so we have the nodes of the system on the rows and the different time instants on the columns. Phi is the modal matrix, whose columns are nothing but vectorized mode shapes. And then here we have this matrix of harmonics, whose rows are digitized harmonic time functions. Now, of course, we could generalize this representation and look for an alternative one that is formally identical, but plays a different role. We have still the response matrix here, and then now we have a matrix, only function of time. We're going to call it the dictionary matrix, and the columns of it, from now on, we're going to refer to them as atoms, because that's customary in this literature. And a matrix A, which contains functions of time, which we call the sparse coding matrix. So formally, identical type of matrix factorization than what we have in modal analysis, but there are some important differences. The main one is the atoms are not subjected to the orthogonality constraints that we typically involve in modal analysis, which implies that we grant ourselves the possibility to work with the undercomplete or overcomplete basis. And also what we would like to do is to learn both DNA simultaneously from the data. Why do we want to do this? It looks like an academic digression, right? Because modal analysis works very well. Well, this would make particular sense if we could somehow tune the search for DNA to capture some features of the response that may be indicative, for example, of the presence of anomaly. For example, some localized features. So what we would like to do is to specify some classes of candidate matrices, let's say script A, script D, with prescribed morphological characteristics that we think apply to our problem, and then limit the search for DNA within these particular classes. All these ideas, now I make them collapse into one big optimization problem, which is the typical dictionary learning problem, which looks like this. We have an objective function that has now two terms. The first term is nothing but a slightly modified least square term. And that controls the quality of the fit. So how good my representation in terms of DNA is. Then we have a second term where I have this one norm, which is known to be a sparsity promoting norm. There is a regularization term that promotes parsimony. Essentially, this controls how A is sparse, which essentially controls how many atoms of the dictionary D I effectively use in my representation, in the reconstruction of the response. So I have here a trade-off between the quality of the fit, the quality of the representation, and the parsimony by which I manage to achieve it. And I control this trade-off through this tuning parameter lambda. And then the most important part, which is the hallmark of our approach, is the fact that here, as you can see, the search for DNA is tuned, is limited within these classes of matrices that we have identified as interesting. Okay, so what's the idea behind the tuned search? Try to equip the atoms of the dictionary with the ability to detect and triangulate anomalies. So the logical part here is the following. The anomalies are spatially localized features in the physical domain. When they exist, we have localized features in the response. And if you look at the data structure of the response, that means sparse objects. So sparse elements in the data structure of the response. So in order to promote the sensitivity of the method to the anomalies, we need to introduce sparsity promoting constraints on the atoms of the dictionary. At the same time, that's not all. Because if we have a representation that is very sparse, it might be good for us, but it might have very little to do with the original data. It might be a very bad approximation of the original response. We also want this to be true. We want also the smooth or the bulk component of the response to be well captured. So we propose a two-dictionary representation, where now we have one dictionary which we call a diffuse dictionary or a smooth dictionary, which is in charge of capturing the bulk part of the response, as if the anomalies were not there. And then we have another one, which is a sparse dictionary, made of sparse atoms, that is in charge of finding the localized features. And as you see, for the sparse atoms, I'm going to introduce this particular constraints on the columns of D. And without making a big fuss about it, I just want to point out that there is a one norm again, which is a sparsity promoting norm, which is going to make sure that the columns of that dictionary will be sufficiently sparse. We don't have to worry about this. This is just an idea of how the algorithm looks like. I just want to point out that indeed we are learning the diffuse dictionary and the sparse dictionary iteratively. And we stop our iteration only when we achieve a sufficiently good level of sparsity in our sparse dictionary. And I also would like to point out that for the individual dictionary learning problem that we're solving here and here, we are relying on some existing software, in particular the software called SPAMS by Julien Mayral and co-workers, which is a MATLAB-compatible software that handles a number of dictionary learning problems. Now, before seeing how this works, I would like to take one slight digression to comment a bit more philosophically on the significance, in my mind, of performing a tuned search. And I'd like to do it using this picture. A picture that captivated me at the very beginning of this journey for me and has inspired me a great deal throughout this project. It's a painting by a Russian painter. It's an example of Russian realism. So the Russian-speaking audience will correct me, but I would say Ilya Ryepin. I hope it's good enough. And it's titled "They Did Not Expect Him." And it's centered around the idea of a family man that comes back home from a long trip and the reaction in the family members or people around the house to his presence. Why is this significant for us? It's significant because in 1967, a Russian psychologist by the name of Alfred Yarbus used this in his seminal work on psychology. He pioneered the use of eye motion tracking to understand psychology of individuals. It's something that I mentioned earlier in the talk. And so what he would do, he would ask patients to take a look at this picture over, let's say, 2 or 3 minutes, and then he would look at what details of the picture they would concentrate their attention on. And he would ask them questions. For example, give me the age of the people, or remember the clothes worn by the people. And he would notice how the patterns that people would follow in observing the image would change in response to what they were asked to provide in terms of an answer. So is this important for us? I just think it's a nice analogy of what we're trying to do. The lesson here is that essentially, as humans, when we look at something, we see what we want to find. We see what we want to see. We have an ability to be inherently directed by our idea of what we are after. So if we can somehow massage our search by introducing element of pre-notion of what are the features that we are after, we can have a better chance to actually indeed finding them. Let's see if what I just said is true. The first example is an illustrative case, so purely mathematically constructed function. We use the first 9 modes of a vibrating plate to construct a smooth pulsating response, and we added to it 2 localized, very, very thin and very, very small amplitude Gaussian spikes that breathe at a certain frequency, which is a blend of the frequencies of those modes. They're so small in amplitude that you don't see them by naked eye. Let me know if you do. That would be anticlimactic, but I have to be open to that. And this is what we obtain with our algorithm. This is a few randomly selected samples of the atoms of the diffuse or smooth dictionary. And you see they are, in fact, smooth features. And these are some samples of the sparse dictionary. And if you look at most of them, you see that they indeed present 2 spikes, very cleanly identified, that correspond to the location of the two spikes that you could not see by naked eye in that breathing or pulsating field. Now, things get a little bit more difficult if we start introducing noise. So here we added some white Gaussian noise. I cannot remember what the dB level was exactly, but pretty aggressive in a sense. And and as you see, the smooth features are still intact for the most part. You recognize a little bit the signature of noise, but not too bad. And but now you see that the sparse atoms, only some of them carry a visually usable signature of the Gaussian spike. Some others only have some other small features that correspond to spikes in the noise. So we have to do something to avoid this type of problem. So one thing we notice is that even if there are a lot of atoms that do not show the anomalies at all, the anomalies are found pretty often. So in a sense, they are very persistently observed throughout the set of the atoms, more persistently than other features. So we would like to now leverage or use this attribute of persistence to guide us in our search. So what we do is we construct what we call a superatom. A superatom is nothing but one single atom that somehow encompasses all the information for the individual atoms of the sparse set. And the way we do it is we partition the domain into regions, and for each region we go through atom by atom, and we see if that particular region is consistently activated throughout the dictionary. If that is the case, then we aggregate information for all the atoms into that particular region. And at the end of the process, only the most persistent regions are awarded. Only the most persistent one appear in the superatom. And so we have that for the noise-free data, we just have one single superatom with 2 blobs that correspond to the position of the Gaussian spikes. And then we have some automatic thresholding code that identifies automatically what is the region that contains them. In the case of noisy data, things are not as clean. We get a lot of action around, but the 2 main blobs are dominant, and therefore we still correctly identify the regions that contain them. Now we move to a problem that mimics the diagnostics problem more closely. This is still simulated, but now we have the simulation of an aluminum plate where I have a point defect right here, and then I have a source right here. And this is what the decomposition into diffuse dictionary and sparse dictionary looks like. These are 3 samples of the diffuse atoms. They essentially are snapshots of the wave field, if you wish. The sparse dictionary, I don't know if you see, but I put some red arrows. There are some pretty feeble but still recognizable signatures of the point defect. However, if I now use the superatom and I aggregate intelligently all the information that I have in here, I come up with this, where I have one blob correlating well with a point defect that gets bigger and bigger throughout the process, and then we correctly identify the region that contains it. Then we try to make the game more interesting by putting 2 point defects, one closer to the source, one further away, and even in this case, we are able to identify both locations. And then we try to look at a point defect that coexists in the domain with the line defect. And we're able to find the region that contains the point defect and find the regions that somehow encapsulate the line defect. So we get a sense of the area of influence of the line defect itself. And then we try to introduce finally some heterogeneity, something that perturbs the clean wave fields that we have used so far. Same simulation of an aluminum plate. The localized anomaly is right here, still a point defect, but now we introduce two stiff ribs. And they act, of course, as strong scatterer. So as you see the snapshot of the wave field goes up, and then there's a strong reflection right here at the first rib. Then something goes through, interacts with the anomaly, and then there's another reflection at the second rib. So we have a lot of activity, a lot of wave field distortion that occurs because of the interference between incident waves and reflected waves. Nonetheless, the method seems to be able to pick up the region that contains that anomaly without being fooled by the other spiky features that do appear in the domain corresponding to the location where the strong stiffeners are. And the second example, we try to mimic something that happens all the time in structural engineering, where we have a crack that emanates from a joint here between the plate and the stiffener. And at the end of the process, we have a similar level of wave distortion, and we are able to identify these two regions that somehow encapsulate the entire length of that vertical line defect. Then I conclude with 3 experimental cases. Here is the aluminum plate, again actuated in the center in the back. In the back there's also this shallow hole, and then I am scanning this part of the front face, and here you see the movie of the wave field. Incidentally, this is the same example that I used before for salience analysis. Diffuse atoms look like this, sparse atoms look like this. Again, with the help of some arrows, I can point to you the signature of the anomaly, which share the domain with a bunch of other spurious ones. And the superatom cleans it up and only gives me one winner, which is indeed the position of this shallow hole. The second example, this is interesting because the way we found it was serendipitous. There was an aluminum plate that had a very thin residual of glue in the back. There was there used to be an actuator that was previously attached to the back of it that had been improperly removed, and there was a little bit of residual glue that about 0.1 millimeter thick attached to the back. And we had forgotten about it. We thought that the plate was pristine, and we were just trying to characterize the plate, see what its pristine response was. And so we excited it, and then we detected there's a wave field with the laser vibrometer. And it looked pristine. Now, a posteriori, we actually looked back at it and we recognized some signature of a scatterer, but not at first. And then, just out of curiosity, we fed it to our algorithm, and this is what we saw. Diffuse atoms, sparse atoms. We have two features in the sparse atoms. One that corresponds to the position of the source, which is itself a localized feature, and then some other things above it, which are corresponding to something else. And the superatom gives us the same picture, the source and something else. And then we went to the back, we inspected it, and we saw that there's a very little elusive residual of glue was indeed located at this particular position. And finally, probably the most powerful example that we recently got, we tried to replicate experimentally the problem of a plate with a stiffener. So this is aluminum plate, excited right here in the back, with a partial hole right here in the back. We are scanning the front in this particular square region. And in the back, we also have this stiffener, and we obtained it by gluing a strip of aluminum to the back of the plate. This is the wave field. You see it looks a little bit different because we were using a different type of actuator, in this case an S-wave actuator. And you see that the wave field is extremely distorted because of the reflections from the stiffener that interact with the wave that we send in. And also because the way this was glued to the aluminum plate was very irregular. There was a layer of glue, probably some nonlinearity going on, a bunch of non-idealities that piled up and produced this highly distorted wave field. Nonetheless, and this surprised us, I have to admit, the algorithm worked significantly well. These are the diffuse atoms, these are the sparse atoms. We cannot make a lot of sense out of this, but the superatom picks a winner, and there's this region right here, which indeed correlates very well with the position of that shallow hole. That's all I have. Let me conclude with some summary of findings. So we embraced an anomaly inference philosophy based on full wave field reconstruction, which we can leverage since we have a device that allows us to sense in this particular fashion. We introduced model-agnostic inference procedures that uses criteria of saliency and sparsity. We think that the algorithm displayed a pretty good performance level, even in the presence of heterogeneity, and they passed the first experimental test. Of course, there's a lot more to be done to see what is the robustness, especially with the more complicated experimental tests. But we believe that the first test was passed. Finally, by mentioning that although we apply this to structural diagnostics, we believe that this could be applied in other fields. Any other field in which people look for anomalies and in which the data comes in the form of a data cube is fair game. For example, we are thinking medical diagnostics, where we have dynamic MRI data that comes in the form of a data cube that is, for all intents and purposes, very similar to the one that we have been using. So we actually think that medical diagnostics might even be like a better, a more powerful arena for this type of techniques. So again, I'd like to acknowledge the work and thank my student, Jeff Druce, my collaborator, Jarvis Haupt, and I'd like to acknowledge the support of a grant by the Digital Technology Center at the University of Minnesota. Here are some publications, some done, some in review, and I thank you for your attention.
If it's...
I forgot.
So my question was before you even started on the second part.
Yes.
But I just wanted to discuss your comment that you said saliency is a generalization of sparsity. And I thought, you know, in saliency, you just do the composition, you do the singular value of the composition, you look for this knee and the singular value, etc. It's kind of a guided, parameterized approach to extracting. So why did you call it generalization? I could use it as a special case of a brute force sparsity.
Yes, I agree with your remark. It's a little bit chicken-egg problem. I mean, which is the mother concept, which is the daughter concept. I think that, in a sense, you can see as a special case of sparsity. I think that where we came from, where we said that was sparsity is like a mathematical concept, and then we were seeing an overarching concept, which was the commonsensical saliency, the visual saliency, the one that humans possess. And so we were saying this is the mathematically implemented, the mathematically describable form of visual saliency. So we were seeing the type of saliency that we can put in mathematical form. But you're right that in a sense sparsity is more abstract as a concept. This would be one manifestation of it.
Could you comment on characteristics of your source? So you didn't say anything about, you know, this source you're using to probe the structure of the material, and I'm sure there's some characteristics.
Right. So I can tell you what we use. I mean, for all the experimental cases, we use transducers. Actually, for all of them but one, we use this like P-wave transducer. So they exert an actuation, a load that is out of plane. For the last one, we used a shear wave transducer that instead tries to breathe in plane and so shears the surface of the plate. That is why you see those perfectly symmetric rings in the first few experiments, like water ripples. And then for the last one, instead, you have that dipolar-looking wave field, because that accounts for the particular way in which shearing takes place.
Is
that what you were looking for?
About the wavelength or the frequency that you're probing,
yes,
and there's got to be some limitations.
Yes, absolutely. All these experiments were performed at either 100 kilohertz or 200 kilohertz. I can be more specific if you don't know which one is which, but that is the range where we were successful with detection. We believe that with this approach, we may give us an extra gear in terms of being able to do something approaching sub-wavelength imaging, looking features that are a bit smaller than what we normally can get with a given wavelength. But I think we are, for the most part, still subjected to the curse of wave-based detection, where we have to have some compatibility between the wavelength that we send in and the characteristic size of the anomalies. I don't think we can elude that problem completely.
All the problems that you presented are two-dimensional. And I understand that conceptually you can extend this for 3 dimensions, but there must be some significant difference between the two.
Yes. Conceptually, you're perfectly right. To me, it's almost one-to-one, the extension. The problem is getting this type of data in a 3-dimensional sense, right? Because we need spatial richness, right? We need a lot of sensing points at all locations. In a 3D sense, that would be also acquiring a sensing location in the bulk. We might not have access to, certainly now with this type of approach. So here we're limited to 2D because we can get something which is spatially rich in a 2D sense with a vibrometer. But with a 3D, it's a different ballgame. What we can think of is, for example, saying now, if we have waves that propagate through the bulk of a 3D object, but I have a surface wave that somehow correlates well with what happens through the bulk, maybe I can infer something about what happens in the interior from a surface wave field. But there's an extra step that needs to be added to the analysis. However, that's why I was talking about the dynamic MRI problem. If we now think about having the ability to look at different layers within a material, and in each one of them induce an elastic or acoustic wave field, then all of a sudden we have a 4-dimensional data cube, right? 3 dimensions in space and time. And that is exactly what people do in dynamic MRI. They look at different levels of depth in the biological specimen that they're looking at, and then they induce a wave field, and they look at it at that depth. So in that sense, you have the type of fully rich data structure in a spatial sense that you would need to apply this paradigm to it. And the problem is that in structural diagnostics, getting that type of data is very difficult. But apparently in the medical field, it's the norm for people who do dynamic MRI. So that's why my concluding remark was that the potentials for this in the medical field might even be superior than in the structural field.
What you've shown is actually extremely impressive. But let me ask you kind of an opposite question. If you would like to design a defect which is the most difficult to detect with your technique, what would you do? So under what condition the method will diverge?
Yeah. What I a little bit sadly recognized working was that there was no black magic in it. So at some point things would start not to work. Because we start getting good results, you feel that it's almost like by some magic. But the idea is it's exploiting a criteria of sparsity. When you start having sparse features that are as sparse of those induced by other objects, then you cannot resolve that ambiguity. So in other words, I can find the anomaly in the presence of the stiff rib, because the stiff rib is bigger. But if I have a benign object that is as small as the malignous one that I'm after, then I cannot discriminate between them. Unless we do something else, unless we detect both, and then we use some a posteriori classification technique to find which one is benign and which one is not. For example, some neural network support vector machine. But then we get into the business of supervised techniques, which is what I was trying not to use. So database-rich or training set-rich techniques. Another enemy, not for the second part, but for the first, is if you don't have any defects at all. Then essentially the first method will give you a false positive no matter what, because it's based on a comparison between features, not on absolute metrics. The second one is immune from that.
Your algorithm.
Yes.
Obviously it's not my field, but looking at how you pose that, it certainly doesn't look like there's any reason to believe that there's going to be a unique minimum, that in fact you aren't even, that it looks like it would be susceptible to even cycling. What general features does your algorithm have in terms of convergence?
First remark is good eye. Good catch. Certainly the dictionary learning problem, not ours, but in general, is first of all a non-convex problem. And the way it is solved, for example, by SPAMS, which is this software that we are relying on, is by breaking it down into two convex problems. So instead of learning DNA, you essentially go through a procedure where you fix D, learn A, then you fix A, learn D, until there is some sort of convergence. So within the convergence that I showed, which was going from one dictionary to the other, each dictionary is solved within a convergence within. Having said that, it's certainly true. It's people in the dictionary learning community are aware of it. They comment on it. There are no guarantees that what you get is a global minimum. And people with very impressive signal processing chops have devised like ideas, rationales to put this in context, but nothing really conclusive. So people have used a pragmatic approach. Sounds rough, but of the idea, if it works, I'll buy it. Here we have an advantage in adopting something like that, which is the following. In a sense, the convergence to a minimum is almost alone for the right for us. It's almost not our primary purpose. Our primary purpose is to have sparsity within a decent level of error in the representation. So we can always check that what we got is indeed as sparse as we want it to be. And then a posteriori check if the error that we made was sufficiently low. What we did is we always checked the error and we made sure that the Frobenius norm of that residual was less than a certain percentage of the original data matrix. But it is heuristics. I don't think there is anything more profound or rigorous that I can say to appease your doubt.
Okay.
Somebody who does chemistry and microbiology, I was pleased to see you talk about both atoms and DNA.
Yes.
My question is one of how computationally expensive is the analysis? You get a wave data from your testing, and I mean, do you get a result in an hour, in a day,
quick.
in a week?
Maybe Jeff can give us some numbers in the back, but I think sometimes it's seconds, sometimes it's minutes, right? Very fast. Yeah, and this is not our doing. This isn't the way so our doing is the mother algorithm, and then the individual pieces is where this non-convex optimization problem is solved, and that's where I guess the algorithmic design comes into play, and it's fast. We think it's competitive. Essentially, compare, for example, to the acquisition time for the data. It's like a tiny little fraction, almost insignificant.
And I think it will be last question.
So don't wavelets help you here at all?
Yes, I was expecting this one as well.
For example, in this specific problem, I could easily see how sparsity in a wavelet domain, and then asking the question, do I have a pattern and something studying out of the pattern? Would do the same job.
Yeah, I actually I think we discussed a bit about this, and I have not tried it yet, but it would certainly be worthwhile because I cannot exclude a priori that they would work. We would just be in a transform domain, and we could still invoke some concept of sparsity. I think that you could keep the framework and just work in a transform domain and see what happens. When we have, I don't know if we would feature the same ability to localize spatially, but it's possible. What I don't have aware of is the performance of wavelets within the presence of heavy noise and heavy distortion. My gut feeling is that the distortion level that I showed in the very last case would not be handled well by wavelets, but I might be wrong. I mean,
wavelets are the prime denoising transformation.
Right. Okay. But then you're talking about denoising and then apply. I mean, here I'm not even trying to noise. I try to work directly on the noisy data. Also because that noise, I don't know if it would be classifiable in a type of noise that is mathematically constructible. I mean, it's not applied everywhere. First of all, it's localized within some regions. It has a temporal dependence. So
that's all good for waves.
That's all good. So let's give it a try. That's all I can say.
So that was the last question of the official part of the seminar. Let's thank Stefano.
Thank you. Thank you.
My problem with the non-convexity isn't the global load. My concern was